In this video, we're going to look at limits. And I want to do so graphically because I think the easiest way to understand or to visualize a limit is to do so graphically at first. I'll have a video later on that shows how to find limits algebraically, but for right now we're just going to take a look at the graphs and determine limits from that. So the first thing to do though is to define a limit, and I'm going to do so very informally. This is an informal definition. There are formal definitions of limits, and again we'll study those later on. But a limit, roughly, is the value a function approaches, and the key is that word approaches. So we know what functions are, we know how they work, and we know how to find their values. So for instance, if I were to label this function here, this graph, label it f of x. I can find any value along this function. So f of 1, I would know that I have to go for find where x is equal to 1, look at its y value, and I see that that is 2. And throughout this video, we're going to assume all values are integer values, they're whole numbers just for the purposes of making it easy. These are all drawn with the intention of being whole numbers. So if it looks a little off, we're going to just round. We can find this function value very easy. We've done this for a very long time. We could find f of 2, f of 3, any of these points we could find because we go to their x value. We can see exactly what that y value is going to be. But what we want to do is we want to separate a function's value from its limit. A function's value, what we just found, is not necessarily the same as its limit value. They could be the same, but they don't have to be. A limit is all about the approach. That is the key. And so if I'm talking about the limit at 1, we are looking at what y value am I approaching as my x's go to 1. So I'm looking still at this point right here, and it happens to be that point, but really we're looking at on this function what happens as my line gets close to this dotted line. So if we look at arrows on either side of that, we can see that to the left we're approaching that 1 point, to the right we're also approaching that 1 point. So it doesn't matter which way we're coming from, we're getting really close to that value. So in this case, the limit value is the same as the function value. It is equal to 2. And so what I can say is let me change that, as x approaches 1, the y value approaches 2. That's kind of long and cumbersome, so we have a more efficient way of writing a limit. This is using a limit statement, and we write lim, L-A-M, standing for limit, and then directly underneath that as a subscript, write x with an arrow 1 indicating that x is going to 1. Then we have to write our function name, f of x. In this case, that limit value is equal to 2. So this x going to 1 here, this x arrow 1, is a subscript. It's supposed to be smaller and underneath that limit, and then the limit and f of x are on the same line. This is my best handwriting on my screen, though. We could do this for any number of values, just like we could find function values. So for instance, if I want to, I could look at the limit as x goes to the 0. So I'm not going to look specifically right at that point. I'm going to look at what happens as we approach that point. So as our arrows are coming in, where are my y values going? Well, they're going to a y value of 1. So limit as x goes to 0 of our function is equal to 1. And we can do this for any number of points, and they're all going to be relatively boring. They're all going to be exactly the same as the function value, because as I head to a particular point, well, that point falls directly on the line, and so the approach is going to be the same as what happens at that point. Let's look at a little bit of a difference here. Let's look at one that's not quite so easy. So here I have the exact same line, but this time I have a hole at that point 1, 2. And so for instance, if I was to say, what is the function value at 1? Well, we'd have to say does not exist. And again, I'm choosing to name this function f of x. I should give it a name. Give it a name of f of x. So the function value at 1, it doesn't exist. That point has been removed with that hole. But we can definitely notice a trend. We are to approach, again, put that dotted line in there for all the x values equal to 1. If I were to approach that dotted line, I can see that it doesn't matter if I'm coming from the right or from the left. If I follow that line, we're approaching that point right there. So what we can say is that the limit as our x approaches 1 is equal to 2. So we didn't have a function value. That point was undefined. However, limits look at trends. Where am I trending to? I don't actually care what happens at that point. I'm trending to that y value of 2. And so we can see, I think, the importance of these things. It's letting us know where we're going, even if we don't quite get there. Or for some reason it's been removed, we can still talk about where a function is approaching or trending towards. So here's an example that we had a point, or a lack of point, where the function value didn't exist, but the limit did exist. Let's look at yet another example. Same line, same hole, but this time I have another point defined right above it. We have the point 1, 3 defined. Let's look for that function value at 1. And we can see it does exist because that dot fills it back in. We see that function value is equal to 3. However, if we look at the trends, right, it's trending to the same spot it was before. Just because we've added that point doesn't mean it's all of a sudden trending there. No, if I were to ignore everything on this line, so let me put that dotted line back in there. If I ignore everything that's happening on that blue line, essentially crossing out that point, it doesn't exist anymore. If I'm looking at where I'm trending back towards that 2. So that's still going to be my limit value. Limit as x goes to 1 for my function f of x is equal to 2. So again, in our minds, we have to separate this idea of a limit from a function. It is completely possible that a limit exists when its function does not. And it's completely possible that both exist, but they're two different values. The approach versus what's happening at that point. Function value, I only care about at this one point what's going on, versus a limit, where am I getting close to? Does this mean that limits will always exist? No, that's not the case either. So let's look at an example there. Here's a piecewise function that I've hand-drawn, calling it g of x, just to give us a different name. Let's start by, and we're all seeing both of these are units of 1. Let's start by looking at that interesting point. I should note that we can find the function value, limit value for any of these points. I've kind of been ignoring the other points, but they're relatively boring because f of 2 is the exact same as limit of 2. That's all like we talked about in the first example. So here we could find the function value, say at 2 if we wanted to. I could find the limit value at 0, but they're going to be the same as a function. Just looking at the interesting things where they don't necessarily match. If I want to know the function value at 1, well, I'd look at what is my y value at 1, and that is 1. But if I look at the limit as my function, or as my x approaches 1, what happens to my function as x approaches 1? Well, now it depends. If I'm approaching from that left-hand side, my y value is going to 0. But if I'm approaching from the right-hand side, my y value is going to 1. And because we have this mismatch, we don't have the same value, that means that the limit fails to exist. If we can't approach from both left and right and get to the same point, that's going to be a point at which the limit fails to exist. If I were to have looked at 0, right, let's just assign this value of negative 1. If I were to look at the limit as x goes to 0, well, there our limit value is equal to negative 1. So sure, this other thing is doing some crazy stuff over here. It's not attached to this other piece. I don't care what's going on over here. I want to know immediately around that 0. As I get really, really close to 0, where am I going? Going to negative 1. As I get really, really close to 0, where am I going? Negative 1. So it doesn't matter if there's other disjoint pieces. It just matters immediately around that section. So if I'm looking at the limit as x goes to 1, immediately around that 1, where am I going? 1. Where am I going? 0. We have that disjoint function, and therefore the limit fails to exist there. So one way we can talk about this is by looking at what's called a one-sided limit. We could talk about from the left or the right. We just couldn't talk about coming from both sides at once. So if I wanted to, I could say, well, let's look at the limit as x goes to 1. This time I'm going to put a little minus on top of it. What that is indicating is we're going to the 1 from the left. You can read it as a negative, but really that means just from the left. So sure, 1 is positive on both sides of it, but if we come from the left, we see that our y values are going to 0. We can also look at what happens as we come at 1 from the right, and we indicate that by putting that positive on top of the 1. That's indicating coming at 1 from the right. Well, here we see that we're going to 1. And so we see that they don't agree, right? And so because these two one-sided limits don't agree, that tells us that the limit doesn't exist. Now, I've been calling these things limits, but what we're really finding here and here, this is a two-sided limit. If you're just asked for the limit and it's not specified left or right and it says nothing about a one-side limit, anytime we see a limit, that is understood to be a two-side limit. So that means we have to approach from both left and right. We can only approach from one side, or if the approaches from left and right don't agree, we can still talk about those one-side limits, but we can't talk about the two-side limit, or we say the limit fails to exist. Let's look at another type of example. I'll call this function h of x. So this is a rational function. We clearly see that it has some asymptotes here. And let's talk about, again, we have lots of boring points. If we're to look at 1, 2, 3, 4, 5, any of these points here, the limit value is the same as the function. Let's talk about the interesting value, which is the 2. X is equal to 2. We do have a vertical asymptote there. I should say negative 2. So if I were to say, what is h of negative 2? Well, we'd say it doesn't exist because there is an asymptote there. But we can talk about the approaches. We're to look at the limit as x goes to negative 2. Well, we do still have a problem there because it depends. We're coming from the left. Well, if we're coming from the left, we can see this is shooting off to infinity. However, if we're coming from the right, we can see that it's going down forever and ever, going down to negative infinity. And so this is another one of those cases we have this disjoint approach. And so in terms of the two-side limit, we'd have to say that that doesn't exist. All infinities are not the same. Positive infinity, negative infinity, going two completely different directions. And so here the limit at negative 2 fails to exist. If we look from either side, we can see that it's going to positive and negative infinity. And here's actually the thing about infinity. When we were talking about a limit, remember our very earliest definition was, what value do we approach? Infinity is not a value. Both of these things are not values here. So really what both these statements here are telling me, the limit fails to exist. Anytime the limit is going to zero, to infinity, that is an example of a limit that fails to exist. So technically, these fail to exist. However, whenever we see that a function goes to infinity or negative infinity, rather than writing the limit does not exist, it is helpful to specify how it fails to exist. Namely, is it approaching infinity or negative infinity? So exactly what I've done here. Really in the back of my mind, I see these and I say, hey, that limit doesn't exist. Those are saying it does not exist. But I've specified where it is going because that more information is always useful. So anytime we see that it's going to infinity, it is a good idea to write that it's infinity, just so we know that those limits actually fail to exist. The reason that those infinities are helpful is because anytime we see that a limit is going to infinity, plus or minus infinity, that is telling us that it is a vertical asymptote. So we kind of looked at this one backwards. We saw the picture, so we knew there was a vertical asymptote. And then we were able to say whether it was going to infinity or negative infinity. But if we're looking at the equations and we see that the limit shooting off to infinity or negative infinity, that is telling us there is a vertical asymptote there. So that will be an important idea, especially as we move into the algebraic equation representations of these things. So we can talk about the y values going to infinity, but we can also look at what happens when the x's go to infinity. All the x values so far, we've had set x values. This time, let's say, or let's find the limit as x goes to infinity. We're using our same h of x function. We could have done this with any of the functions. So here I'd have to look at what this value is approaching. And what we see is as that line continues on indefinitely, what we know is true about rational functions, it will approach its horizontal asymptote. And so we'd see that it has a approach of 1. As that thing goes on indefinitely, it's going to get closer and closer to that horizontal asymptote. We could also look at the limit as x goes to negative infinity. In this case, it'll be the exact same thing. As we go backwards forever and ever, we're going to get closer and closer to that same value of 1. And for rational functions, we know that those horizontal asymptotes should point in the same direction both ways. It's not true for all functions, right? If we think about a exponential function, has a horizontal asymptote on one side, it does not approach the horizontal asymptote on the other. It could be a piecewise function, that wouldn't be true. And then we could just look at things that are, not rational functions where they don't have a horizontal asymptote. So for instance, if we look at this example right here, the one we kind of started with, we could look at that limit as x goes to infinity too. And what we'd see is that it's going to infinity itself. So yet another example where the limit fails to exist, but we've also specified in the way it doesn't exist. Both positive and negative infinity don't exist, going to the two different places. But it is helpful to be able to find that limit as x goes to infinity or negative infinity, because if we do see that it goes to a value, that is going to be our definition for horizontal asymptote. So again, we kind of looked at this thing backwards. We know what a rational function looks like. We know its properties. So we know it had a horizontal asymptote there. But when we formally define vertical and horizontal asymptotes, which keep in mind, never did a formal definition of those back in pre-calculus. When we look at their formal definitions, we're going to see that they rely on these limit statements. Vertical asymptote exists whenever we are looking at the limit as x approaches a value, and we see that limit goes to infinity or negative infinity. That is the definition of a vertical asymptote. Or if we take the limit as x goes to infinity or negative infinity, and we see that approaches a value, that's going to give us a horizontal asymptote. So the key to limits is separate in our minds a function value from its approach. The limit is about the approach. The function value is what the y value actually is. We've seen that we can have a function value and not a limit value. That was true of the last example. We can have a limit value but not a function function value. That was true of the previous example. And in the very first example, we can have both and they could be the same. We could have both and they could be different. So just keep in mind, limits are not the same as function values. Limits are all about the approach. The function value, we want to know what happens at the 1.